November 2025, Baytown, Texas. ExxonMobil pauses what would have been one of the largest clean hydrogen plants ever attempted, 1 billion cubic feet a day. And the CEO's explanation is refreshingly blunt. They could not find customers willing to sign contracts for the stuff. Now here is the part that made me sit up. That same month, on that same site, ExxonMobil signed a joint development agreement with BASF to build a completely different kind of hydrogen plant. One that runs on exactly the same natural gas and never produces a single molecule of carbon dioxide to capture. Same company, same feedstock, same patch of Texas dirt, two opposite answers 30 days apart. I spent over a decade commercializing first-of-a-kind energy technology, and that is the kind of thing that tells you more than any press release. When the company with the best information in the business quietly hedges against its own flagship project, pay attention to what it is hedging against. So here is the verdict up front. Blue hydrogen is the cheapest low-carbon hydrogen on the board. It is cheaper than green by a lot, and it is losing anyway. It is a real bet in exactly one configuration, which I will define precisely, and a fantasy everywhere else. And the reason has almost nothing to do with hydrogen. Because making hydrogen was never the hard part. Splitting methane is 19th century chemistry. The hard part is the carbon. Every time you break that molecule apart, you are left holding a pile of carbon, and it does not disappear. It only changes form, and it changes address. There are exactly three things you can do with it. You can bury it, you can sell it, or you can give up on hydrogen and just burn the gas for electricity, because somebody will definitely buy that. Blue hydrogen is answer 1. Turquoise hydrogen is answer 2. And answer 3 is quietly winning, which we will get to because it involves a data center. Everything here is public data. There's a free one-page verdict plus the cost workbook, the one where you set your own gas price and capture rate, and watch the answer move, waiting for you at bankable.show, link below. Two numbers to hang on to today, 60 and 6. I will explain both. Let me show you the graveyard first, because it is remarkable how fast this happened. 8 months, 4 projects. ExxonMobil's Baytown plant paused in November. In the United Kingdom, BP withdrew its H2 Teesside project on the 1st of December. 1.2 gigawatts, an application that had been grinding through the system since March of 2024, pulled days before the government was due to decide. And Air Products, the industrial gas company, halted its blue hydrogen plant in Louisiana and put the carbon capture and ammonia pieces up for sale. And then there is the fourth one, which is 30 minutes from my house. Air Products announced a net zero hydrogen complex outside Edmonton, Alberta in 2021, $1.3 billion, running in 2024. Today, that project costs $3.3 billion and starts in late 2027. The company has it filed internally under underperforming assets, and the incoming CEO used a word you almost never hear from a public company about its own flagship. He called the failures partly self-inflicted, costs more than doubled. Schedule slipped 3 years, and they are still building it because they already have customer contracts. Hold that thought because it turns out to be the whole answer. Now, none of this is a technology failure, and I want to be careful here because that is the lazy read. Steam methane reforming is over a century old. It is not experimental. It makes something like 95% of the world's hydrogen right now, today, and it does it profitably at $1.50 to $2.50 a kilogram. Bolting carbon capture onto it is not science fiction either. Shell has been running the Quest facility at Scotford in Alberta since 2015. It has put something like 9 million tons of carbon dioxide underground. It works. It has worked for a decade. So if the technology works and the economics are the best in clean hydrogen, why is the industry canceling projects? Let me show you the plant, because the answer is visible in the process flow. Take a steam methane reformer. Natural gas and steam go in, and over a nickel catalyst at around 800 degrees, you get hydrogen and carbon monoxide. Shift the carbon monoxide with more steam, and you get more hydrogen and carbon dioxide. Now you want to capture that carbon dioxide, and here is where it gets awkward, because it comes out in two completely different places. There is the process stream, which is concentrated, high pressure, and genuinely cheap to capture. And there is the furnace flue gas, the exhaust from burning gas to heat the reformer tubes, which is dilute, atmospheric, and expensive. Most blue hydrogen plants capture the first one and vent the second, which is why conventional steam methane reforming with carbon capture captures around 60% of the carbon, not 90, 60. That is not a plant running badly. That is the design. There is that first number, 60. You can do better. Capture the flue gas too, and you can reach around 90% at real added cost. Or you switch technologies entirely to autothermal reforming, which moves the combustion inside the reactor using pure oxygen, so there is only one concentrated carbon dioxide stream to deal with. Most autothermal projects target 95% capture. That is why essentially every serious new blue hydrogen project is autothermal, and why that technology goes from roughly nothing today to a projected 37% of blue hydrogen production by 2030. So the engineering has an answer. Good. Now the harder problem. To call blue hydrogen genuinely low carbon, the clean hydrogen standards want somewhere around 90 to 95% capture. Operating facilities today typically hover around 60. And when the Institute for Energy, Economics, and Financial Analysis reviewed 13 operating carbon capture projects worldwide, most of them came in below their 90% design rate, and some failed outright. But the capture rate is not even the wall. This is. Natural gas is mostly methane and methane leaks out of wells, valves, compressors, pipelines. And methane is a monster in the short term, more than 80 times worse than carbon dioxide over a 20-year window. So the carbon footprint of blue hydrogen depends on a number that happens hundreds of miles upstream of your beautiful new plant. Here is what that does. At a low leakage rate, say 0.4%, a plant capturing 60% lands around 4 kilograms of carbon dioxide equivalent per kilogram of hydrogen. Push capture to 90% and you get down to about 2. Good. Now set leakage to the American average, roughly 1.5%, and capture 100% of the plant's carbon. Perfect capture. A capture rate nobody has ever achieved. You are still above 2.5 kilograms. Read that again, because it is the whole episode. Past a certain amount of upstream leakage, improving your capture rate stops fixing the problem. The binding constraint walks out of the plant, which the developer controls, and into the gas field, which the developer usually does not. This is where the famous fight comes from. In 2021, Howarth and Jacobson published a paper arguing blue hydrogen's life cycle footprint was more than 20% worse than just burning natural gas for heat, and only 9 to 12% better than ordinary gray hydrogen. The industry responded furiously, and their objection was specific. Howarth and Jacobson assumed 3.5% leakage and used a 20-year warming window instead of the conventional 100-year one. And here is the thing I want you to take away, because it is more useful than picking a side. Both camps' arithmetic is reproducible. They are not arguing about math, they are arguing about inputs. Which means the honest way to look at blue hydrogen is not as a number, it is as a sensitivity. And that sensitivity is precisely the investment risk. Okay, does it pencil? On raw cost, blue wins. The International Energy Agency's 2026 review puts gas with carbon capture in regions with cheap gas at potentially just above $1 a kilogram. They flag it as theoretical, with no live project achieving it at 95% capture, and that caveat matters. but the broader range for blue is roughly $2 to $3.50 a kilogram, against gray at 1.5 to 2.5, and green from a Western machine at around 5. So blue lands about $1 a kilogram above the incumbent. That dollar is the entire commercial question, and policy very nearly closes it. In the United States, the 45Q tax credit now pays $85 a ton for carbon stored underground. A steam methane reformer emits roughly 9 to 12 kilograms of carbon dioxide per kilogram of hydrogen. Capture 9 of those kilograms and, at $85 a ton, that is about 77 cents a kilogram of hydrogen delivered as a tax credit. Roughly 3/4 of the gap closed by the government, which tells you what blue hydrogen actually is. It is not a hydrogen business, it is a carbon credit business with a hydrogen plant attached. The molecule is nearly incidental. The credit is the product, and that is exactly why it stalls. A tax credit closes a cost gap. It does not manufacture a customer. Nobody is under any obligation to pay extra for a molecule that is somewhat cleaner than the one they already buy, and when Exxon's CEO explained the Baytown pause, that is precisely what he said. No committed offtake. So, second answer, what if you never make the carbon dioxide in the first place? That is, turquoise hydrogen, and the chemistry is beautifully simple. Instead of adding steam and oxygen, you just heat methane until it falls apart. Methane goes in, hydrogen comes out as gas, and the carbon comes out as a solid, a black powder. No carbon dioxide is produced in the process, so there's nothing to capture, nothing to compress, nothing to inject, and nothing to monitor for the next 100 years. It deletes the entire problem set I just spent 10 minutes describing. And the energy numbers are genuinely striking. Splitting methane thermally takes roughly 7 to 12 kilowatt hours per kilogram of hydrogen. Electrolysis, the green route we costed last time, takes 50 to 55. BASF and ExxonMobil put it plainly in their announcement. Methane pyrolysis needs about 5 times less electrical energy than water electrolysis, and it uses no water at all. This is not a lab curiosity either. A company called Monolith has been running a commercial-scale plant in Nebraska since 2020, producing roughly 2,500 tons of hydrogen a year and around 14,000 tons of carbon black. And there is a Canadian one. Back in 2022, the gas utility FortisBC, Suncor, and an Australian technology company called Hazer started a methane pyrolysis pilot at Suncor's terminal in Port Moody, British Columbia. That one is still moving. This March, Hazer brought in the engineering contractor KBR specifically to accelerate it, with FortisBC set to own and operate what would be the first commercial-scale plant of its kind in North America. And the Baytown demonstration is targeting up to 2,000 tons of hydrogen a year. So, cheapest energy input, no capture problem, real companies building real units. Why isn't this the answer? Because of the second number, 6. Look at the chemistry again. Methane weighs 16, the carbon in it weighs 12, the hydrogen weighs 4. So every kilogram of hydrogen you make this way leaves you with exactly 3 kilograms of solid carbon. You do not get to choose. It is stoichiometry. And you can see it in Exxon and BASF's own specification for that demo plant. 2,000 tons of hydrogen, 6,000 tons of carbon. 3 to 1. Now, that carbon is worth money. Carbon black is a real commodity that goes into tires and pigments and batteries. It is a market worth roughly $20 billion a year. And that is where turquoise economics live or die, because the published cost estimates range from about $1.50 to $3 a kilogram, and the single biggest swing factor in every one of those studies is what price you assume for the carbon. So let's test it. The world consumes on the order of 18 million tons of carbon black a year. Divide by 3 kilograms of carbon per kilogram of hydrogen. 6 million tons. The entire global carbon black market can absorb the byproduct of 6 million tons of hydrogen a year. The world uses about 100 million tons of hydrogen a year, 6%. Turquoise hydrogen can decarbonize about 6% of the world's hydrogen before it floods its own byproduct market. Past that point, the carbon stops being revenue and becomes a disposal cost, and every one of those cheerful cost estimates inverts. A peer-reviewed analysis this April said exactly this, that the mismatch between potential carbon supply and realistic market demand creates a fundamental risk of oversupply that undermines the economic assumptions underneath the techno-economic studies. So look at what we have. Blue hydrogen's constraint is geological and political. You need a permitted sink, a capture rate you probably will not hit, and a policy regime that has to hold for 12 years. Turquoise hydrogen's constraint is arithmetic, and arithmetic does not negotiate. One honest caveat on that ceiling, and it comes straight from the Canadian project. Port Moody isn't aiming at carbon black at all. It's aiming at synthetic graphite, which is a much smaller market but a far richer one, and it is the single strongest argument against the number I just gave you. Treat it as a real option and an unproven one. Nobody has yet shown battery-grade graphite coming out of a pyrolysis reactor at commercial scale, but if somebody does, the 6% moves. One more thing about turquoise, in fairness, it runs on natural gas too, so that upstream methane leakage problem, the one I said was the real wall, turquoise inherits it completely. Pyrolysis fixes the reformer. It does not fix the gas field, which brings me to where these things actually work, and the pattern is clean enough to be a rule. Every blue hydrogen project that died in those 8 months was a greenfield plant looking for new customers, and the ones proceeding are not. Shell took a final investment decision on Polaris at Scotford, adding roughly 650,000 tons a year of capture next to a refinery it already owns, on a site where it has been storing carbon for a decade, feeding a molecule it already makes. Air Products is finishing its over-budget Alberta plant for one reason, which is that it already has the contracts. And there's a third Alberta data point sitting right in the middle of this that I haven't mentioned. In 2021, Suncor and ATCO announced a 300,000-ton-a-year blue hydrogen plant at ATCO's Heartland Energy Centre near Fort Saskatchewan, same industrial park as the Air Products complex. A final investment decision was expected in 2024. There still isn't one, and the province's own major projects registry now says the plant might start in 2029. Nobody has cancelled it. It just hasn't been able to close for 5 years running, which is the pattern in one line. Greenfield plant, no committed customer, no decision. So the rule is, blue hydrogen works as a retrofit on an existing molecule next to a permitted sink for a customer who already exists. Change any one of those 4 and you get the graveyard. And turquoise works when you stay small enough for the carbon to remain a product, which is why the leading company in the space is, honestly, a carbon black manufacturer that gets hydrogen as a co-product, not the other way around. Now, follow the money, because the policy map is genuinely strange. In the United States, blue hydrogen support is 45Q, $85 a ton of carbon buried. And the same bill that preserved it also raised the credit for carbon used in enhanced oil recovery to the same $85, creating parity between burying carbon and using it to push more oil out of the ground. In Canada, the structure is different in a way I find revealing. Blue gets the carbon capture investment tax credit, 50% of the capture equipment. Turquoise gets the clean hydrogen investment tax credit, 15 to 40%, scaled purely by measured carbon intensity, and methane pyrolysis was made eligible for it at the end of 2024. So Canada subsidizes blue for the machine that buries carbon, and turquoise for how clean the hydrogen turns out to be. Turquoise has no capture rate to miss, and no sink to permit, so it clears that bar more easily. And then there is Alberta, where a lot of this is supposed to happen. The industrial carbon price is $95 a ton. But the credits that actually settle compliance have been trading far below that, in the neighborhood of $20, which means a project that pencils on $95 carbon and clears on $20 carbon is not really a project. It is a subsidy application with a schedule attached. So, the verdict. On the Bankable scorecard, blue hydrogen comes out in the mid-4s out of 10. Maturity is strong at 7, and that is genuine. The economics score 6, the best in this entire hydrogen series, because the cost advantage is real. But scale up is a 3, the moat is a 4, and timing is a 4, and those 3 are all the same finding, wearing different hats. There is no buyer. Blue hydrogen is a real bet as a retrofit with a sink and a customer. It is overhyped as a new energy vector, and the 4 dead projects are not an opinion, they are the market saying so out loud. Turquoise is worth watching. It solves blue's carbon problem honestly and elegantly, and then runs into a ceiling at roughly 6% of world hydrogen demand. And answer number 3, the one nobody planned? When BP walked away from H2Teesside, it was not beaten by green hydrogen or by Turquoise. The site had been earmarked for an artificial intelligence data center instead. Same land. A buyer who signs contracts today at a price nobody has to be persuaded into. That is what actually outbid blue hydrogen. And here is the detail I cannot stop thinking about. Monolith, the turquoise company in Nebraska, is reportedly looking at building a data center on its own plant campus. One company lost its site to compute, the other is inviting compute in. Same force, opposite responses, and I suspect that tells you more about the next 5 years of industrial energy than any hydrogen roadmap will. Your 2 numbers, 60, the capture rate the fleet actually delivers when the standard wants 95, and 6, the percentage of world hydrogen turquoise can clean up before its own byproduct market saturates. The free 1-page verdict and the full cost workbook are at bankable.show, and the workbook is the interesting one here because you can set the capture rate and the gas price and the carbon price yourself and watch which of these 3 answers survives your assumptions. As always, I am judging technologies and economics, not companies and not securities. Nothing here is investment advice. So tell me in the comments, bury it, sell it, or skip it. Which carbon answer would you actually underwrite with your own money, and what would you need to see first? There is plenty more hydrogen to take apart, and plenty more ways to power a data center. You pick what is next. If this was useful, subscribe, and I will see you in the next one.